All right, let's take a look at 2014 E&M number 3. This is the electrostatics question, and it being number 3 is probably an indication that it is hard. Take a look at the density function that they've given us, where if you're inside alpha, you have this density function, which is a combination of inverse square and exponential decay. And then if you're outside, it's 0. So if we take a look at the nuclear charge only, and you have to keep in mind that the nuclear charge is a point particle positive Q at the center of the atom, and then this density formula refers just to the electron. So if we're looking at the nuclear charge only, what we get is plus Q going straight. That doesn't change because as you move away from, so if we put a plus here and that's our point particle, and then what we have is out to radius alpha, so out to radius alpha, we have an electron cloud. So as we move away from the center along this blue line, and we have our imaginary sphere enclosing more and more volume. Think of concentric spheres as they get bigger as you move R out. We're not going to be enclosing any more positive charge. It's always going to be at its maximum value. Now the electron charge, first off, electrons are negative. Second off, once we get to radius alpha, we've enclosed all of the electrons. The idea being once you're outside the atom, there's no more parts of the atom out here where I put my blue dot. So all these blue, this is empty space. So we're going to have an asymptote here. And what we're going to have is an exponential down decay curve where when we start at the center, we've enclosed the nuclear charge, but we have not enclosed any electrons. So it's starting out at 0, and then it's going to be an exponential decay kind of curve. And then once we reach alpha, that's as good as we're going to get. Now I'm going to have to pause and scroll down and delete. All right, I moved my graphs up because if you take a look here, what they want is a graph of the electric field. So if we don't have any electrons, then this dashed line is the electric field due to just the nuclear charge. But once we add in electrons, we're going to be reducing the electric field because we have a plus and a minus here. That's going to reduce the electric field. Remember, E equals K, our most basic formula for the electric field. KQ, and this has to be net. So we have plus Q, we have minus Q, and when we add those together, the electric field is going to be reduced. What we also need to keep in mind is that once we've reached alpha here, we have a minus Q for the electrons and a plus Q for the protons, and the net is going to be a 0 when you get out of the get out past alpha. And other than that, it's going to be reduced to be, let's see if I can draw this, to be inside or closer to the origin than that dashed line is, because we have extra negative charges that's going to make the electric field smaller. All right, part C, use Gauss's law. Okay, so pause here for Gauss's law. Gauss's law being Q enclosed over epsilon naught, integral of electric field dot dA. And both of those guys are ways of calculating and describing the electric flux. So for C part 1, calculate the electric field at R greater than alpha. Okay, so R greater than alpha, and we'll just pick an arbitrary radius here and draw a line down through these guys. At R greater than alpha, we have plus Q from the nucleus and minus Q from the electron cloud. So Q enclosed equals plus Q plus a minus q equals 0. So what that means is then that the electric field is going to be 0. All right, part 2. R is less than alpha. Well, now Q enclosed is going to be the result of doing some calculus. And the only part here that we have to care about for the calculus part is the electron cloud, because the rest of it is just going to be just add in the nuclear charge. And the electron cloud, remember, that guy's negative. So figuring out the integral part, and we'll focus on that. Let's put this guy over here. So the negative Q, because of the electrons, is going to be rho dV. Now rho they gave us. Rho is going to be beta over r squared e to the minus r over alpha. And they told us that it is spherical. Did they tell it? They had to have told us that it was spherical. Where is it? Point particle. There's at the center. Distance from the center. They do say Gaussian sphere. So they've told us that we're using a sphere here. So by telling us that we're using a sphere, and let's get this back in the right place. All right, by telling us that we're using a sphere, we know that the surface area of a sphere is 4 pi r squared, and to turn that into a volume, sort of like a balloon that you're blowing up, you add in a dr. So putting these guys together into the integral, we're going to have things cancel out, which is a happy thing. So r squared e to the minus r over alpha, then we have 4 pi r squared dr. Now, that r squared and that r squared are going to cancel, and beta and 4 pi are constants, so they're going to get moved out. So let's clean this up. This is going to be the same integral, just rearranged a little bit. So we're going to have 4 pi beta integral e minus r over alpha dr. And now we have just an exponential decay to have to integrate. And they're telling us that r is less than alpha. So that means we're going to go from 0 to r. And when we integrate this, we're going to have an extra negative sign, which, remember, we should have a negative sign here. Sorry, I dropped it. Negative sign here. We're going to have an extra negative sign. That cancels things out. And we're going to end up multiplying by alpha because we have to divide by 1 over alpha. So this guy becomes 4 pi alpha beta e to the minus r over alpha. And our limits are going to be 0 and r. And this is important to include both limits, because when you plug in 0 for r up here, the whole thing doesn't go to 0. It goes to 1, which makes this guy 4 pi alpha beta parentheses 1 minus e to the minus over alpha. All right. And you also need to keep in mind that this whole thing is negative. It's electrons. So when we come back over here to Q enclosed, we're going to have the nuclear charge minus 4 pi alpha beta 1 minus e to the minus r over alpha. That is our Q enclosed. Our area for Gauss's law, they told us it was spherical, so that will be 4 pi r squared. And when we substitute these guys back into Gauss's law up top here and solve for E, doing a little bit of algebra, we're going to have Q enclosed divided by epsilon naught divided by the area. So Q minus 4 pi alpha beta 1 minus e to the minus r over alpha all over 4 pi epsilon naught r squared. And remember that r squared is from the area. Okay, part D. Based on the model, what is the physical meaning of the constant alpha? Okay, let's take a look back at this constant alpha. Suppose we let, so D, let R equal alpha. What happens then to this whole expression? So if R is equal to alpha, we have alpha over alpha, and that's 1. And we've enclosed all of the electron's charge, 100% of it. And that means our Q enclosed is all of the charge that's available to this atom. So R equal to alpha is the radius of the atom. Because once you get outside of that, you've enclosed all of the charge and there's nothing left. And what you see is an electrically neutral atom. And I'm pretty sure they hinted at that back up here. Scientists describe an electrically neutral atom. So this is an attempt at a mathematical model that will give us Q enclosed is equal to 0 once we get to the radius of the atom, which is alpha.